In section 3.8, we're going to talk about implicit differentiation, which is a process for differentiation that's used when we have a relation between two variables, usually x and y, but we are not able to solve for one in terms of the other. So I just took these learning objectives from the book. It's 3.8.1 says, find the derivative of a complicated function by using implicit differentiation. That would be better stated as a complicated relation, because these are not always going to be functions that we're differentiating, but you'll see how this will go. And then the second is use implicit differentiation to determine the equation of a tangent line. And again, for a relation that's defined between two variables. So first we need to talk about the difference between implicit and explicit form of an equation. So if we look at 3xy minus 2y equals 5x, the current form for that equation that I just underlined is called implicit form, because it implies a relation between the two variables, but it doesn't directly say what one is in terms of the other. We certainly could solve this for y, though. If you think about how to do that, you would factor out a y on the left side, and then you can solve for y just by dividing by 3x minus 2. So we can see that y is a function of x, and y would be 5x over 3x minus 2. So this is called explicit form, because it tells us explicitly, here's what y will be if we know what x is, right? So the other form, like we said, was implicit form, because that relationship is implied, but it's not stated explicitly. So in this section, we're going to learn how to find dy dx, even if we're not able to explicitly solve for y in terms of x. So a familiar equation that we'd usually leave in explicit form would be the equation of a circle of radius 1 and center 0, 0. So we know x squared plus y squared equals 1 would give us just the circle with radius 1, center 0, 0. Right? So for that curve, certainly y is not a function of x, because this doesn't pass the vertical line test, and also x is not a function of y, because this doesn't pass the horizontal line test. So we aren't able to solve for one variable or the other without a positive or negative in front of a square root, but we can certainly express this relationship implicitly like this: x squared plus y squared equals 1. So we will be able to use the methods of this section to find the equation for the tangent line at a point on a circle, even though we don't have y as a function of x. So the key behind what's going on here is to assume that y is defined implicitly as a differentiable function of x. And that would be the case if we imagine this circle here and we take any little snapshot, small window of that curve, we would see that y is a function of x for that small area. So it's legal to assume that y is a function of x because it is in any of these small windows. So here's what we're going to do, the problem-solving strategy for this process called implicit differentiation. The first step is take the derivative of both sides of the equation, and then we're keeping in mind that y is a function of x. So when we do our derivatives, we have to use the chain rule to differentiate. So they give us an example here. The derivative of sine x with respect to x would be cosine of x. But if I'm differentiating sine of y, I would first differentiate the outside function, and that would give me cosine. I would leave the inside the same, and then I would multiply by the derivative of the inside. So if I'm differentiating a term that's like sine of y, I want it to end up as cosine of y times dy dx. we'll have that extra factor of dy dx anytime we do the derivative of a term that has a y as its input. Once we've done all the differentiation, then we're going to add and subtract. It says rewrite the equation so that all terms containing dy dx are on the left and all terms that do not contain dy dx are on the right. And really, it doesn't matter which side is which. You just want all the dy dx terms on one side, all the non-dy dx terms on the other side. And then whichever side you have all the terms with dy dx, you'll factor out the dy dx and then divide to get your solution. So let's start with that unit circle. Familiar curve. Right, so we'd have circle radius 1, center 0, 0. And this is telling us to find dy dx. So I'm going to take the derivative of each side with respect to x. So I'm not actually differentiating in this line. I'm just saying, here's what I'm going to do. I'm going to take the derivative of this side with respect to x, and I'm going to take the other derivative of the other side with respect to x. As we work our way across, we would have the derivative of x squared, which would be just 2x, and then plus the derivative of y squared with respect to x. So here's where we're going to need the chain rule. We'll say, well, the derivative of the outside function would be 2, and then I'm going to times whatever the inside is, so 2y, and then multiply by the derivative of the inside, which is dy dx. So when I'm differentiating the y squared, since that term involves a y, once I'm done with its derivative, I will have a dy dx involved. And then on the right side, now I have derivative of 1, and that should be 0 because 1 is a constant. So we can now solve for dy dx. Our next step says rewrite so that all terms containing dy dx on the left and all terms that do not contain dy dx are on the right. So I need to get this 2x out of the way. So I'm going to write 2y times dy dx equals negative 2x. And then I only have one term that has dy dx in it, so I don't need to factor dy dx out. I can now just divide by 2y on both sides, and I will be done. So dy dx is opposite of x over y, because these factors of 2 will reduce. Notice that dy dx depends on x and y. We're used to our formulas for the slope depending only on x. That will be the case when you have y as a function of x, but in a situation like this, where x and y are defined in terms of each other only in an implicit way, our formula for dy dx will involve typically both of the variables. Let's pick a point on the unit circle, maybe over here, a quarter way through quadrant 2, right? And that point on the unit circle would be negative square root of 2 over 2, square root of 2 over 2. So if we think about the slope at negative square root of 2 over 2, square root of 2 over 2, we will get opposite of x, so square root of 2 over 2, divided by y, square root of 2 over 2, so we should get 1. And that seems like it is probably good, right? It looks like the tangent line there would probably have slope 1. So at least from picking on that one point, we can see our formula for dy dx looks probably fine. Okay, next up, find dy dx if x equals sine of y. So we differentiate both sides. with respect to x. And that looks like the derivative of x on the left and the derivative of sine y on the right. So again, I'm just marking down what I want to do, and then I will go ahead and do the derivatives. Derivative of x with respect to x would just be 1. Derivative of sine y, here's where I need the chain rule because y is the input instead of x. So I differentiate the outside function, which would be the derivative of sine, so cosine, and I leave the input the same. And then I multiply by the derivative of the inside, which I would write as dy dx. And then I solve for dy dx, and I have dy dx would be 1 over cosine of y, which is the same as secant of y, so I could write it either way. So here, the slope depends only on the y-coordinate. Let's think about what the graph of this looks like. X equals sine y should be the graph of y equals sine x, just reflected across the line y equals x, right? If it were, let's see, so y is like our angle here, and x is the sine value. So it's everything turned kind of on its side. We know that sine values only go between 1 and -1. And we know that the sine of 0 is 0, and we know that the sine of pi over 2 is 1, and sine of pi is 0. So we know this is going to go like that, and we know how the sine function looks. Once we have that part of the curve, we can extend to the rest. So that's what this curve would look like. Let's find the slope at this point, 0 pi. So dy dx at the point 0 pi would be secant of pi. And cosine of pi is -1, so that would be 1 over cosine of pi, which is 1 over -1, so -1. And it's certainly believable that the slope is, it's clear that the slope is negative. -1 is believable. I wasn't careful at all about my scale on my axes. So 1 tick mark in the x direction is not equal to 1 tick mark in the y direction. But I'm sure this is correct. So the slope there will be -1. All right, then, example 3. Find dy dx if y times the square root of x plus 2 equals xy squared plus 5. So we had y times the square root of x plus 2 equals x times y squared plus 5. And my first step is to do the derivative of both sides with respect to x. On both sides I have a product, so I need product rule on both sides. So when I do product rule, I do the first factor times the derivative of the second, and I'm just going to map this out. So y times the derivative of x plus 2 in square root plus the second times the derivative of y, derivative of the first. And on the right side, I'll have the same thing. I just have a product for the derivative of xy squared, but then plus the derivative of 5. So the first times the derivative of the second plus the second times the derivative of the first. plus the derivative of 5. So again, this derivative of notation that's just d dx in front of whatever you're trying to differentiate is really helpful here, so you can kind of just map out a plan and then actually take the derivatives. But now if we take the derivatives where we have indicated that we're going to, we'll say, okay, x plus 2 in a square root, that's the same as x plus 2 to the 1/2. So just rewriting that and rethinking that in our brains. We'll have y times, here I'm going to need the chain rule because I have a function inside the square root, not just x inside the square root. So I do the derivative of the power 1/2, which will be 1/2, leave the input the same, and then subtract 1 from the exponent. Multiply by the derivative of the inside, which is just 1. And then add square root of x plus 2 times the derivative of y with respect to x. And that is exactly just dy dx, right? The derivative of y would be 1, multiplied by the derivative of the inside, which is just dy dx. And then we have x times the derivative of y squared with respect to x. And right there, we're going to need a chain rule again. So we'll do 2y times dy dx. And then we have y squared times the derivative of x with respect to x, which should just be 1, plus the derivative of 5 with respect to x, which is 0. So let's pay attention to the derivatives where we needed that extra step. So when I did the derivative of y, that was right here. And when I did the derivative of y squared, I have 2y dy dx. So those were the interesting derivatives. And notice those are the terms now that we want to make sure we move to the, or not move to the other side, but get grouped together. So I want this term and this term to be grouped together. Remember, term means the things that are separated by addition. So the pieces that are multiplied with the dy dx, I want to keep those with the dy dx. It's just anything that's added to those groups I want to move to another side. So let's see, I'm going to get everything with the dy dx on the left. So I'm going to have square root of x plus 2 times dy dx. That's going to stay on the left. And that other group that I just put an orange rectangle around, that's going to need to move. So I'm going to subtract it from both sides. So I'm going to subtract 2xy times dy dx. And then on the right, I'm leaving the y squared where it is, but I'm subtracting the group on the left that had the y over 2 times x plus 2 to the negative 1/2. So I need to move that whole group. So now we have everything that has a dy dx on one side, everything that doesn't have a dy dx on the other. And then we can factor out dy dx. And once we do that, we've got one factor of dy dx in two terms. So I factor that out. Dy dx will be multiplied by square root of x plus 2 minus 2xy. And that should be equal to, let's see, y squared minus, I'm going to rewrite this a little bit, y over 2 times the square root of x plus 2. And then we just want to divide by this factor that is now multiplied with dy dx. So I'll have dy dx equals the y squared minus y over 2 times the square root of x plus 2 that was there on the right side, and now divided by the square root of x plus 2 minus 2xy. It's probably okay to leave it in that complex fraction if we wanted to clean it up, which is always better. I would look for the denominators, and there's only one denominator here. All the other denominators are just 1. So I would multiply in the numerator and the denominator by that expression. So cleaning this up, we're going to have to distribute. And let's see what we got. So we get dy dx equals, let's see, we'd have 2 times y squared times the square root of x plus 2 minus y, because when I distribute to that second term, the 2 times the square root of x plus 2 in the numerator and denominator will reduce to 1. So that would be my numerator, and in the denominator I would have 2 times x plus 2, because when I multiply the square root of x plus 2 with the square root of x plus 2, I will just get x plus 2. And then we'd have minus 4xy times the square root of x plus 2. All of those factors that are outside the radical would get multiplied together, and then the radical would be multiplied with that group. So there's a cleaner version of dy dx. On the next page, we will start looking at equations of tangent lines. We did a little bit of this just beyond what was actually asked in the examples in the first two, but here we're actually asked to find the slope of a tangent line at a specific point, 3, 3. So our relation and relating the x and y in example 4 is y cubed minus 3y squared minus 2i plus x squared equals 3. So I'm going to take the derivative of each side with respect to x. And on the left side, I have 3 terms that involve y. So I can tell that for each of those, when I do the derivative, I'm going to need a multiplied by dy dx at the end of it. So derivative of y cubed with respect to x will be 3y squared times dy dx. Derivative of 3y squared with respect to x would be 6y times dy dx. The derivative of 2y with respect to x would be just 2 and then times dy dx. And the derivative of x squared with respect to x will be plus 2x. And on the right side, we should just have a 0 because the derivative for a constant is 0. All right, then we want all the terms that have a dy dx on one side, all the other terms on the other side. So I need to subtract 2x from both sides. And once I've done that, then I can factor out dy dx. So I will have 3y squared minus 6y minus 2 multiplied with dy dx. And on the other side, I still have my negative 2x. Then I want to get dy dx by itself, so I will divide by 3y squared minus 6y minus 2. So there's a formula that gives us a slope at any point as long as we know the x and y coordinate. But we want specifically the slope at 3, 3. So the slope at 3, 3 would be negative 6 over, let's see, 9 times 3, so 27 minus 18 minus 2. I'm just filling in 3 for x and 3 for y. So let's see, that comes out to negative 6 over 27 minus 20. So negative, it'd be positive 7. So negative 6/7 for the slope. Just to check this in GeoGebra, let's find the equation then of the tangent line at 3, 3. So I would do y minus y1 equals m x minus x1, and the m is what we just found, the dy dx. So we'll have negative 6/7 and x minus 3, and on the other side we'd have y minus 3. So if we want to solve this for y, we would have y equals negative 6/7 times the group x minus 3 plus 3. So unfortunately, with a graphing calculator, we are not able to graph or plot implicit relationships like this. So for this, you'll need either GeoGebra or Maple. So we'll talk in class about how to use Maple to plot an equation like this and to find dy dx actually using Maple, and then to plot the tangent line. But for now, I'm going to just demonstrate in GeoGebra because that's actually really easy too. So let's do y cubed. Get the plot of the function first, or the relation, y cubed minus 3y squared plus, oops, I lost my minus sign here. Okay, so y cubed minus 3y squared minus 2y plus x squared equals 3. All right, so there's our plot. And then we wanted the equation of the tangent line, which was y equals, I can type it as y equals, I'm just going to type it as negative 6/7, since this actually is a function, times x minus 3 plus 3. And it looks like that is perfect, right? It looks like the 0.33 is there, and the slope looks just like we would want it to look. So everything looks fine. All right, next up, find the equation of the tangent line to the graph of x squared minus sine xy plus y cubed equals 1 at the point negative 1, 0. So again, we want to first just find the derivative of each side with respect to x. So I'm just writing down that my plan is I'm going to differentiate both sides with respect to x, and then I'm going to maybe highlight everywhere there's a y because I know that's where it's going to get a little bit complicated. So first I'll do the derivative of x squared, which is just 2x, and then I want to subtract the derivative of sine of x times y. Notice sine of x times y, I'll need the chain rule because there's a function inside sine, but I'll also need the product rule because the inside function is a product of two factors, not just one. So I'm going to do the derivative of the outside, which would be cosine, and leave the inside just the same. And then I'm going to multiply that with the derivative of x times y. So I'll need the first times the derivative of the second, which I would just write as dy dx, plus the second times the derivative of the first, which would just be 1. So all of that is the derivative for sine of xy. And then I still need to add on the derivative of y cubed. So I'd have 3y squared times dy dx, because there was a y as the input for that cube function. And then lastly, on the right side, I will have 0, because the derivative for a constant is 0. And this is the first time I think that we've needed to do some distributing before we could add and subtract terms from both sides. So what I need to do is first distribute this cosine across that addition, and then I can start adding and subtracting terms. So I have 2x minus, I'm going to write x times cosine of xy times dy dx plus, minus cosine of xy times y. Should have put that y in front just to make sure it doesn't slide into that cosine function by accident. Plus 3y squared dy dx equals 0. So now I can see that this 2x does not involve dy dx, and this y times the cosine of xy does not involve dy dx, so those need to move to the other side. So on this side I'm going to keep negative x times cosine of xy times dy dx, and, oops, I'm going to keep 3y squared times dy dx. And on the other side, I'm going to subtract 2x, and I'm going to add y times the cosine of xy. Then I will factor out dy dx. And I've got next to that then x times cosine of xy with a negative sign plus 3y squared. And then we have dy dx will be negative 2x plus y cosine xy divided by negative x cosine xy plus 3y squared. So quite a bit of work just to get to the derivative, and this will give us the slope of the tangent line. So the slope of the tangent line at the point negative 1, 0 will be dy dx at negative 1, 0. So we're filling in negative 1 for x, which means I'm going to have positive 2. We're filling in 0 for y, which means we'll have 0 times cosine of 0, which will just be 0, divided by, let's see, we have a negative 1 for x, so 1 times cosine of 0 plus 3 times 0, which would be 0. Cosine of 0 is 1, so this is going to simplify to 2 over 1. So we're coming up with a slope is 2, and we actually want the equation of that line. So the equation of the tangent line at negative 1, 0 should be, let's see, y minus 0 equals the slope, so 2 times x minus negative 1, so times x plus 1. So y equals 2 times the group x plus 1. So let's take a look again at GeoGebra and plot that equation and the tangent line and make sure everything looks good. Take those two out of the picture, and so now I have x squared minus sine of x times y. So x squared minus sine of x times y plus y cubed equals 1. That's good. That curve looks just like it should. And then the equation of the tangent line was y equals 2 times the group x plus 1. And that looks great too. So looks like we did everything just correctly. One last example asking us to find the equation to the tangent line of the graph of this equation at the point 4, 2. So we'll differentiate both sides with respect to x. Again, just writing down the plan. And when we differentiate the left side, the outside function is the squaring function, and then the inside is a sum that in which one of the terms involves y. So we just need to be careful of our plan here. So the 3 will get carried along, And the derivative, when I differentiate the squaring function, I would have 2 times the inside function to the 1, and I'm not going to write to the 1. And then I need to multiply by the derivative of the inside. And since that's the sum, I need to make sure that I get parentheses around this group, because I want to make sure that I get the first set of factors multiplied with the derivative of the inside, the entire derivative of the inside. So the derivative of the inside will be 2x from the derivative of x squared plus 2y times dy dx. And you want to be really careful that the dy dx is only multiplied with the 2y, not distributed to the 2x, because it should be just with the derivative of y squared, not with the derivative of x squared. So this is exactly how you want your left side to look. And the right side will be similar, but I just have 100 times this group. So I'm going to have 100 times the derivative of x squared minus y squared, which will be 2x minus 2y times dy dx. And now I'm going to distribute. I will have, let's see, I'm going to multiply this whole group with the 2x and with the 2y dy dx. So that's going to give me, it looks like 12x times x squared plus y squared plus 12y times x squared plus y squared times dy dx. And on the other side, I will have 200x minus 200y times dy dx. And now that everything is distributed, I want to make sure that I move terms around. This term does not have a dy dx, nor does this 200x. So those two I want together on one side, and then the two terms that have dy dx I want together on the other side. So I'm going to leave the dy dx's on the left. So I'll have 12y times x squared plus y squared times dy dx. And then I want to add the 200y dy dx to both sides. And then on the left side, oh, that's going to be the right side now. I'm going to leave the 200x, and I'm going to subtract 12x times x squared plus y squared, that whole group. Then I will factor out dy dx. And that will be multiplied with 12y times the group x squared plus y squared plus 200y. And then my last step will be to divide. And I suppose we'll need to finish this by filling in a specific point and getting the slope and writing down the equation. So we'll have dy dx is 200x minus 12x times the group x squared plus y squared divided by 12y times the group x squared plus y squared plus 200y. So I can see there are some factors of probably 4 that I could factor out of there. I'm just going to leave it just like that. No, I'm going to divide everything by 4 just to get the numbers to be a little bit smaller. So if I factor a 4 out of the numerator, I'll have 4 times 50x minus 3x times x squared plus y squared. And if I factor a 4 out of the denominator, I'll have 4 times 3y times x squared plus y squared plus 50y. And then I can reduce those 4's. So here's a nicer looking formula for dy dx. All right, and now that we have that, we wanted the equation at the point 4, 2. So up here. So dy dx at 4, 2. So 4 for the x's, that's going to give me 200 in the numerator minus 12 times 16 plus 4, so 20. And in the denominator, I'm going to have 3y, which is 6, times x squared plus y squared, so 16 plus 4, plus 50y, so plus 100. So that works out to 200 minus 12 times 20 is 240, divided by 6 times 20, that's 120, plus 100. So it looks like I'm getting negative 40 over 220. I can see that's negative 4 over 22, so negative 2 over 11. So that's the slope. And the equation then of my tangent line, I would have y minus 2 was the y coordinate equals the slope times the group x minus 4, which is the same thing as y equals negative 2/11 times the group x minus 4 plus 2. So last thing to do here, let's just take a look at GeoGebra and make sure that everything looks right. All right, so turning off our old things here. So we have 3 times the group, x squared plus y squared squared. So there's one side, and that is supposed to be equal to 100 times x squared minus y squared. So there's the picture that we're looking at, and now we want the equation of the tangent line, which we came up with as y equals negative 2/11 times the group x minus 4 plus 2. So that looks just like we'd like it to look. Looks like we did everything just fine. And I think that's the end of that section. So hopefully you're seeing how this process works for implicit differentiation. We'll certainly get more practice with this in class.